Okay, so we should be on this page here, and we're going to continue with what we were talking about last week, Friday, where we kind of went over like what is a function, but we really worked a lot with it algebraically. Like we were plugging things into our functions, we were setting our functions equal to solve for things, and we did talk briefly about how does this relate to geometry, okay? But today we're still going to talk about functions, but I'm going to kind of switch gears a little bit, and that I'm not really going to be focused so much on plugging numbers in. There might still be some of that we have to do, but today I want it to more look like visually, what do these functions start to look like? And what do they start to look like in geometry? Okay, so let's just remember from what we talked about last week on Friday what a function is. So remember on Friday we talked a lot about input versus output and being able to talk about like being able to recognize the difference between those when you're looking at your function notation. Okay, so a function, if you remember the technical definition up here, it's when you have these two sets, input and output, that are related to each other. And every member of the input has something to go to in the output. So in technical terms for like algebraically, we talk about things called like domain and range. Okay, domain would be like the set of all your x values, and that's right down here. And your range would be all of your y values. Okay, now sometimes they may not write domain and range on these problems. They might say like set A, set B, but whatever set comes first, that's usually your domain. And then whatever set comes second, that's going to be your range. When we think about that on a graph, and we're talking about like x and y values, maybe we're looking at specific points that came from a line. And so all the x's would be put into my domain column, and all my y's that would like directly connect would be put into my range. Okay, but let's talk about what this looks like on a picture, and if I don't have numbers to work with. So down here, they're going to give you these sets. And if you notice, like they don't have any numbers on here. Like they don't say A, B, and C, D, E, and F are like given numbers. That they could be. They could be any numbers that you wanted them to be. But right now, they're just kind of keeping it generic for us with our points. Okay, in order to understand what a function is, like we've talked a lot about it in the math terms, but let me give you an example that maybe you'll be able to relate to, okay? When you guys leave this class, you're all going to go to advisory next today, right? Because it's an advisory day. Do any of you happen to go to the same advisory next period? Okay, maybe a couple of you have the same advisory teacher, okay? Do any of you, though, like next period, try to go to advisory and try to go to like science? Or do you have to pick one? You might go to advisory in like a science classroom, okay? But it doesn't mean that you're learning science in advisory. So if you think about what that means like for us, if we were in a function, we all can only go to one location when we leave this room. Some of you will stay here because I have some of you in my advisory, but we don't do any math when we're in advisory in here. So I'm not thinking so much about subject-wise. And even if that's a little bit confusing, think about your class that you go to after advisory. Some of you will go to English. Some of you will go to science, Spanish, PE maybe, study hall. Okay, and some of you, again, might still have those classes together. But are any of you ever trying to go to history and English at the same time? Do any of you go to like an English teacher and a science teacher at the same time? No, you have to pick. You can't split yourself into going to two different locations. Just like after school, you either, go home, or maybe you go to a friend's house, or maybe you go to work. Okay, but you can't do all of those things at the same time. You can't be at work and be at home and be at a friend's house at the same time. You have to choose a location to go to. We can't split ourselves into two people and go to two different locations at the same time. So when you think about that, apply that to this math idea. When we're looking at numbers in our domain, they can only go to one location in your range. Some of them might go to the same location, and that's okay, because some of you guys might go to the same class together later. But it doesn't work if our domain values are trying to be split and to go to more than one location at one time. So if you look at this first example here, number 1, it's got set A and set B. Remember, set A is your domain, set B is your range. If you look at points A, B, and C, do you see how they each have an arrow coming off of them? So that's just telling you where they go. So A is going to D, B is going to E, C is going to F. Okay, this could mean A is going to science, B is going to English, C is going to PE. Okay, so it's just saying each one's going to their own location. Are any of those points A, B, or C trying to go to more than one place at one time? No, they all have one location that they're going to. So if we're asking ourselves, is this a function or not, we're going to be able to say yes, because here's why. Each element in set A goes to 1 in set B. Okay, again, nothing in set A is trying to be split. A is not being split. They all have one arrow coming off of them to show where their location is going. So now if you guys look at number 2, is the same thing happening here? Is everything going to one location? What do you think, Lloyd?
No.
What's the issue here?
A is trying to go to both D and B.
Yeah, A is trying to be split. A is trying to go to Spanish and English at the same time. Okay, you have to pick. You're either going to your Spanish class or you're going to your English class. You don't get to do both at the same time. Those two teachers are not going to meet in the same room and have the same lesson for you. So you're going to say no to this one. And yes, our reason over here is because A is going to D and G. C is not the problem. C is going to its own place, and that's fine. C is not trying to be split, but they are trying to split A. That's what causes this an issue right now. And so it's not considered a function. It's a different type of situation going on. If we were to actually look at graphs, like if you look at graphs from algebra and like what you're going to see next year in Algebra 2, there's ways to decide if something is a function by looking at the graph. So this is still something that exists. I'm not saying that this isn't like a real thing. This is just not considered to be a function anymore because of how it behaves. What do you guys think about number 3? Do you think this one's a function? Keegan, what do you think?
Yeah, because every X is going to its own Y.
Yeah, it's okay. Sometimes it confuses kids. Like B and C are both going to F. Okay, but that's like the example I gave. Some of you might go to the same advisory next period, and that's okay. Or, all of you are in here in math together, but I don't know what you had first period. You probably all were in different classes, or maybe a couple of you had someone from your first period that you were with, but now you're all here together. So it's okay if we all go to the same location. Just like it's all okay that we're all in math, or if we all went to Walmart after school, or we all went to the football game or something like that, that would be okay, because we're not trying to split our places here. And my reason why, I'm just going to arrow down, I'm not going to rewrite all of that, but it's the same thing as what we said before. Everything in set A is going to a location in set B. Nothing's trying to be split. So what do you guys think about number 4? Yes, it's a function? Yeah, same thing. Okay, this time they're both just going to the same place, and that's okay. Is there a really easy way to determine if something is a function or not by just looking at the picture? What do you think, Parker? What are you using to determine that maybe in the picture? The arrows. Okay, if something has more than one arrow coming off of it, it's not a function. That's kind of the quick, easy way to do that. So I'm going to say a point in the domain has more than one arrow means it's not a function. If everything has one arrow, everything's fine. But you can see on number 2, the reason why we said no to that is because of A. A is causing the issue there because it has 2 arrows that are trying to come off of that one point. Okay, so now looking at 5, 6, 7, really quick, to take 30 seconds or less, circle yes or no, and if you think those are functions or not. So what do you guys think? Number 5, yes or no? Good. 6? No, what causes the issue there? The 2. The 2 has more than one arrow coming off of it. Number 7
Yes.
is a yes. Good. All right. So again, that's a very algebra idea. Okay. When you're looking at things like that, you're looking mainly at numbers because you even saw on those examples, instead of saying like letters like A, B, and C, they did throw in numbers. But you still handled it the same way. Like you were still trying to decide if they were functions by just simply looking at those arrows. Okay. So now let's talk about how does this apply to geometry. So we have things in geometry called mappings. Okay. A mapping is very similar to what a function is. It's showing how the domain values or my input values relate to my range values or my output values. We talked on Friday about how in geometry, instead of saying input output, we say pre-image and image. So the same thing is kind of applying here. If I'm looking at my shapes this time, I'm not necessarily looking at a graph with like numbers or points in it. I'm looking at 2 different shapes. I can decide if something is a mapping or not by understanding where are these letters from this shape going to the letters on the second shape. So to kind of help us do that, I'm going to write this out. Now you'll kind of start to see a shortcut, just like we saw a shortcut with the arrows up above, that you won't have to do all of this every single time. But this is going to help you kind of understand what makes something a mapping versus not a mapping. So down here, we have 2 pictures. And they're telling us that for all of them, really, so for 8, 9, and 10, and 11, they're all saying that the pre-image is that triangle KLM. So that's not changing. They are just changing the picture of KLM a little bit for 8 to the rest. But that first triangle, that one that's kind of blue, that's your original shape is what they're saying. Now, the second shape that they give you or the second thing that they give you, that's the image. So that would be our output. We want to decide if it's a mapping. So think about what we talked about with functions. It holds true here for a mapping. A mapping is only going to work if and only if each member of the pre-image corresponds to one and only one member of the image. So again, I can't have anything from my pre-image trying to be split. So if I look at number 8, what I like to do is list out the points on my pre-image first. So my pre-image points are K, L, and M. Then I like to list out my points for my image. So that's the second shape. So in this one, it's that purple triangle. So those are N, O, and P. If I wanted to kind of show this as like domain range and like have my arrows in, I could decide how I wanted to do this. Like K could just go to N, L could go to O, and M could go to P. Okay, I don't have to set it up that way. I could have K going to P, I could have L going to N, and M going to O. I could kind of rearrange those arrows if I wanted to. But the key thing is there, guys, did any of my letters K, L, or M have more than one arrow coming off of them? No, because everything from the pre-image got used over there in the image. Everything had something to go to. So if they're asking, is this a mapping, we're going to go ahead and say yes. Okay, and why? It's very similar to what we talked about up above. Each point in the pre-image goes to 1 in the image. So for the rest of these 3, we're starting with the same pre-image shape, KLM. So for 9, 10, and 11, I'm going to do something very similar here. I'm going to write out K, L, and M. Now what's going to change is the image. So the shape that they're giving you is going to switch a little bit here. For number 9, what letter should I write down for my image? Yeah, T, S, U, V. And it doesn't matter the order, guys. Okay, so let's try to draw our arrows. K could go to T. L could go to S. M could go to U. I need something to go to V, and what's going to happen? Yeah, there's going to be more than one arrow that comes off of one of the points. Does it matter what point I do it to? No. But the issue here is that one of these points is going to have to get split. So let's just do M because it's closest. This is not a mapping. Okay, and because I'm going to say L, K, or M has to be split. I chose M, but you could have chosen any other letter, K or L, and done the exact same thing. But the issue is that there were 4 points that we were trying to go to, and I only had 3 to start with, and so one of them was going to have to split. Okay, how about number 10? What are my points for my image? Q and R. So K could go to where? Q. L could go to Q2. M could go to R. Is that an issue? No. Do I have more than one arrow coming off of K, L, or M? No. So it's a mapping. And again, I'm using the same reasoning. Each point in my pre-image goes to one of my image. I'm just drawing an arrow because I don't feel like writing that all out again. Okay, 11. What's my point from my image? T. So what's going to happen here? All 3 of them are going to go to T. Just like there's, a whole bunch of you, but we could think about there's 3 of you that are in the same math class right now. Okay, now there's more than that. But if we think about in the context of this, that's okay. You all are allowed to be in here at the same time. Okay, so this is a yes. And again, same reasoning. Okay, so maybe you guys are looking at this, and I don't necessarily need to see you guys writing out those letters all the time, but maybe you're starting to understand there's like a connection between your pre-image and your image here, and why we said yes on some and we said no on number 9. So what I want you guys to do is flip the page over, and there's these 3 at the bottom of my screen here, 12, 13, 14. Really quick, I want you to just circle yes or no if you think that it's a mapping. What do you guys think for number 12? Yes or no?
Yes.
Okay. 13 and 14?
Yes.
Okay. What's a quick, easy way to decide that? Are you raising your hand straight?
Yeah.
Go ahead.
Just count the dots.
Count the dots. So you count the dots on your pre-image and you count your dots on the image. What has to happen in order for it to be a yes? Agree?
It has the same number of dots or fewer.
To start with? To end with. So in order for it to be a mapping, a quick way is to count your dots, like Stryker said. And then if you look at the 2 numbers, they have to either be the same or the second one has to have fewer points. Okay, or you could also think the first one has to have more points in order for it to be a mapping. Okay, so up here I'm going to write my image, or not my image, sorry, my pre-image has the same or more points. That means that it's a mapping. But good, you don't have to write out the letters like we did. I mean, you can, and you can draw all those arrows if you want to, but it's a lot faster if you just count the dots and you can make that connection. So the reason why 13 was a no is because on the first one, the purple one, that has 6 points, and on the green one, there's 7. So one of the 6 is going to have to get split. Okay? Questions on that? Okay, so now, if you guys look at this next thing here, when we talk about functions, there's like a special kind of function that we're going to look at, and it's called one-to-one. And we've already seen one-to-one functions show up earlier in our notes, okay? So in one-to-one, everything has one unique location to go to. Nothing is being shared. Everything has one arrow off of it, so it's still a function, but nothing is like going to the same place. So if you look at these ones here, set A and set B, you can see how each point has one arrow and it's going to one location. Now, the second example, it's still a function, but it's no longer one-to-one because both B and C are trying to go to the same place. Okay, and that's okay. That's still a function, but it's no longer one-to-one. Now, in geometry, we have the same thing happening, but it's called a transformation. If you have a shape, and that would be your pre-image, and then you have another shape that looks similar to it, that's your image, and they have the same number of points from start to finish, that's going to be called a transformation. Okay, so like up above, we saw some where they didn't have the same number of points, like number 12. There wasn't the same that we started with and ended with, but it was still going to be a mapping. Okay, but like on other ones, when they have the exact same number of points, like right here, you can see that we started with 4 and we ended with 4. That's going to be a one-to-one function, but in geometry we call that a transformation. The second one is still considered a mapping because I had 4 and I went to 3, but it's not considered a transformation anymore because they don't have the same number of points. Okay, so a transformation must have a pre-image and an image with the exact same number of points. Okay, so number 15, is it a transformation? No, because I don't have the same number of points there. 16? No. 17? Yes. Good. Any questions on that?